Now it's time for hands-on session. So I would like to invite Professor Mohan L. Verma sir and Mr. Narendra Kumar sir for hands-on session.
Good afternoon, everyone. And this is the last hands-on session of this international workshop. So, in this hands-on session, we will discuss about, we will learn about how to plot, how to run pdos and bands, especially related to electronic properties, as well as we will try to run charge density plot if time is available, if that candidates do fast. And then finally, some properties we have to discuss, especially that optical properties. And it was good covered by Dr. Radhya ma'am. So this is the content for today's hands-on session. So now mic is handed over to Narendra. So Narendra, are you ready?
Yes, sir.
Okay, so let's start.
So, welcome all in this day 3 hands-on session. Can you see my screen?
Yes.
Yes, sir.
Okay, so today first we will summarize what we did yesterday, and then we will plot band and pdos, DOS as well. So yesterday we did cutoff, mesh cutoff optimization, then K point, lattice, and then final optimization. So we had one script here that is script cutoff, and in this script, what we did, we have our input file. First, we vary our mesh cutoff, then the K points, and then our lattice constant. Yesterday, I forget to copy my FDF file to that script. That's why we had a wrong density of state. So this is only one script in all the folders. What you have to do, you have to copy your FDF file and modify it according to that script. The main motive is just to vary our mesh cutoff, then your K points, and then your lattice constant, and then do the final optimization. So today I will be do the final optimization. Just open the day 2 folder and then go to T2. Here I will be do here in outside all these directory. So before running this final calculation, I just want to point out two things here. One is these lines that is for bands. I will explain it after the Siesta calculation. And then these tag that is for projected density of state, or you can say the projected density of state. First, I am explaining this flag. This one is comment. This is our minima, and then the maxima, and point between minima and maxima, how many points I want to plot density of state. And this one is the sharpness of that peak that we were trying yesterday. So for PDOS, you need to add this flag in your FDF file. This flag is also available in the tutorial. If you see that T2 tutorial, you need to add these lines in your FDF file. Okay. Now I already added these lines, and these lines I'm for now let me comment these lines. If I want to comment something, comment means the program will not read those lines. So what I will be do? I will be add hash key here, hash 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 okay. Then save your file. Save it and cross. Then open a terminal here. And you have to run Siesta first. How you will be run Siesta? Simple command Siesta less than your input file name, that is carbon.fdf. Then you can use this sign t and log.out, your output file name. Siesta, your input file name, and this sign t log.out. Press enter. Okay, done. Press ls. So here to plot the density of state, you can use the utility eig2dos. You can use another utility fmpdos. So first, let me do it with eig2dos, or you can plot a file directly. This file dos file. When you add these flags, the pdos flag in your FDF file, uh, another file is created with the extension of .dos. You can directly plot it, or you can convert this file, eig file. It is somewhere here. It is eig. You can convert your eig file to DOS. You can plot DOS from here, or I will explain another utility fmpdos later. But first, let's plot this DOS directly. So for that, you can, what you have to do, xmgrace, then your file name, that is siesta.dos.
Narendra,
Yes, sir.
your slide is not moving, I think so. It is not changing. I'm just watching the first screen only. What's about the others?
Same here.
Okay, let me reshare it again.
Risha.
Can you see it now?
Yeah.
Okay, sir. Now the terminal is opened here. Hello.
Terminal is open, but same screen is there. XMGrace sister.dosh. It is.
Yes, yes. Actually, I connected through any desk, so I have two screen there. So if I
Okay.
change like this,
Okay. Okay.
yes. Now you can see, sir, the screen, the DOS file.
Yeah.
So here, this, just sir, give me 1 minute. I need to Yes. So what you have to do to plot the DOS, XM Grace, Siesta.DOS, and your XM Grace will be open. If you can see, sorry. So this is your DOS, but you have to shift the Fermi here. To shift the Fermi, you have to open a file that is EIG to DOS.
Sir, actually,
Yes.
one terminal is covering the presentation, your presentation, sir. Please minimize the terminal.
Now, can you see it now?
No, sir.
1 minute. Let me know now, sir. Can you see it now, sir?
Yes, sir. Yes, sir.
So, can you see the XM Grace as well? Grace.
Yes, sir. Yes, sir.
Okay.
Just to repeat the method you have adopted.
Okay, sir. Let me repeat it. For DOS, what we have to do, we have to add a flag in our FDF file, that is this flag pdos. Am I audible?
Yes, sir.
And you can see my screen, right?
Yes, sir.
Yes, sir.
I opened the carbon.fdf file. Can you see it?
Yes, sir.
Okay. For DOS or pdos, you have to add this flag in your FDF file, where this first is -20, that is your minima, and next is your maxima, and the sharpness of the peak, and the points between your minima and maxima. And then save it and cross, open terminal, and run the Siesta here. Done. When you run the Siesta, you have two options to plot a density of state. One, you can directly plot the DOS file, this file, siesta.dos. When you add these flags in your FDF file, this pdos flag, a DOS file will be created in your directory. You can directly plot it using XMGrace, or you can convert your EIG file to DOS. So let's try the both. First one is XMGrace. First one is the DOS. To plot the DOS, what you have to do? You have to hit XMGrace, then siesta.dos and enter. Okay. Now this is your DOS, but you have to shift the Fermi energy here. So how you will shift the Fermi energy? Just minimize it and open your EIG file. If you see in your EIG file, you have energy here. That is the Fermi energy. in the DOS, we need to shift this energy. So how you will be shift? This is very important point. You have to go data, then transformation, and evaluate expression. I'm repeating it again. You have to go data, transformation, and evaluate expression. Here, select this column and this one. Then you have to enter a formula that is X is equal to X plus your Fermi energy. That is, it is 5.0471. 5.0471 3426. And when you apply or accept, either do apply or accept. Don't do both. Otherwise, your Fermi energy will shift 2 times. Either press on apply or accept. I'm going here on accept. Done. Now you can see your Fermi energy here. I think data, transformation, evaluate expression. X is equal to X is equal to X plus, then press apply. The formula is X is equal to
ये बेटी को डाउनलोड करना है
the formula is X is equal to X plus your Fermi energy, that is 5.0 something. Should I repeat this step again, or you get it? Okay, now I'm moving with the second option, that is EIG to DOS, that we tried yesterday. We will convert this file, open in terminal, using EIG to DOS. EIG to DOS, then minus F to shift the Fermi energy. But here, if you are using this DOS file to plot your density of state, then you need to shift your Fermi energy manually. But here, using this command minus F, that means this program EIG to DOS automatically shift your Fermi energy. Minus S, the sharpness of the peak, that is 0.2. Then minus N, the number of points. You can use 1000, 2000. Then minus N, minus M, your minima, let's say minus 20. Then your capital M, minus capital M, your maxima, let's say 5, or you can say 20. Then your EIG file name, that is siesta.eig less than dos.dat. Enter. Now a file dos.dat is created here. This one dos.dat. If you plot it, you can get the same density of state that we got using this DOS file. It should same xmgrace dos.dat. It is something similar like that one. If you increase the number of points between these points, you can play around the sharpness, the point, minima, maxima, and you can see the change in your DOS peaks. Okay, now the next one is FMP DOS. FMP DOS is mainly for to plot the individual contribution of atom. Suppose you have a system in that you have different kind of species like gallium arsenide, and you want to see how much is gallium contributing, how much is arsenide contributing. For that, you have to plot pdos, or projected density of state. To plot the pdos, we will use another utility, FMP DOS. So where it is FMP DOS, you have to go into your Siesta where you installed, and then the util, and find for FMP DOS that is inside this contrib, a curve. Open terminal here. First, I'm going to clean it. Then type make. I'm repeating it again. You have to go inside the Siesta, then util, and then contrib, and a curve, and open terminal here and type make, because I already did it. So it is saying nothing to make. Okay, now ls, you can see you have FMP DOS utility here. So copy this FMP DOS to your user local bin. So how you will be copy sudo cp FMP DOS to usr local local /bin. Let me paste it in the chat box. And hit enter. It will ask for your password. Enter your password. And done. Okay, now let's go back to our working directory. Here. Okay. Now we copied FMP DOS to user bin, so we will directly use FMP DOS. FMP DOS. Then hit enter.
Then FMP DOS
Sorry. So FMP DOS, now it is saying for your input file name. So let me type ls. When you run a Siesta using the flag that we added in our FDF file, here you have another file that is pdos. You can see siesta.pdos file is here. So type fmpdos first. Then it is asking for input file name, that pdos file name. So here, what is our input file name? Siesta.pdos. So you have to enter siesta.pdos. pdos is in capital, pdos. pdos. Hit enter. It is saying your output file name. Let's say you want to plot the total density of state pdos. I'm writing total underscore dos dot that. Hit enter. Now it is saying the chemical label or number of atom or number of species. So here you can, because you are doing total, or here if you see the instruction, it is saying 0 for all. 0 for all. We are doing all, total. So we will enter 0. Enter. Then it is asking for n, your principal pointer number. And here, if you see the instruction 0 for all n, then I'm pressing 0 again. Enter. ls. Now you can see a file that is total dos.dat is created here. Plot this file. It is similar like your DOS or EIG to DOS file. Okay, now the important thing is here. You have a carbon. Okay, here you have carbon, and electronic configuration of carbon can be 1s2, 2s2, and 2p2 here. So we want to see the contribution of these 2s and 2p. So for that, the n or principal quantum number is, for let's say for 2s, I'm writing it again. I want to see the contribution of carbon 2s. In that case, and my principal quantum number is 2, and L, your orbital quantum number. For S, what is the orbital quantum number? 0. Because L is 0, 1, 2, 3, S, P, D, F. Here we have S, that means L is 0. If we have P, let's say for 2P, if we have here 2P here, in that case L would be 1, not 0. If we have 2P, then L would be 1. So let's do it in our FMPDOS. To run FMPDOS, your input file name, is siesta.pdos. Now I want to plot first carbon 2s. So carbon 2s dos.dat. Hit enter. Now the species is carbon, so you have to hit carbon, the symbol carbon C. Enter. N is for 2s. N is 2, and L, your orbital quantum number. For S is 0. Hit enter. Now it is saying extract data for M. Your M is principal, orbital, and M is what is M? I forget. It is magnetic quantum number. So it is saying 0, 9 for all M. So we need all magnetic this. So you have to hit 9 and enter. Now if you press ls, you can see a carbon 2s dot dash dot dat file is here. We will plot this file in one XM grace, but let's do for 2p as well. Our input file name is siesta dot pdos. Enter. Next is carbon 2p dot dos dot dat. Enter. Again, the species name is carbon C. Enter. The N is 2p. So 2 for P. L is 1. You can see here L is 1. So 1. Enter. And magnetic is all. And 9. You have to press 9 for all M. Now let's plot these files. We have carbon total density of state, then carbon 2p and carbon 2s. Let's do it in XM grace. Enter. This is my XM grace. Let's go to data, import, ASCII file. So first one is total density of state. Okay. Then the second one is carbon 2s. Press OK. Then the carbon 2p. Press OK. Done. Now, first thing we need to shift the Fermi energy. Go to data, transformation, evaluate expression, select Control A, all these lines, all these sets you have to select. And again, the same formula, x is equal to x plus your Fermi energy. X is equal to x plus your Fermi energy. What was the Fermi energy? Let me check it again. There is EIG file. There is. It is 5.0. I'm repeating it again. To shift the Fermi energy, where you have to go, data, transformation, evaluate expression, and select all the sets from this side and this side as well. Just click on any one of it and press Control A. Similarly, from this side, Control A. Then you have to enter a formula, that is x is equal to x plus your Fermi energy, that is 5.04713426. And make sure here you have too many zero. Here either press on apply or accept. If you press apply, then close it. Let's like apply and close. Do not hit on apply and accept both. You have to either click on apply or accept. Now let me set the range. If you double click on x-axis and set the range, let's say from -10 to 5. Okay, and major spacing, let's say 1. This is our density of states. No. Press apply, and let me give the name as well. How you will be give the name? Just double click any one of it. The first one was our total DOS. Press apply. The second one is our carbon 2s. This is pdos. Then the third one is carbon 2p pdos. Now you can decorate it, like you can change the color, you can increase the width like this. This total. The second one is red, carbon 2p. Then third one is, let me do it blue. Okay. Now here you can see this is your total density of state of our graphene sheet. In this, carbon 2p is contributing more as compared to carbon 2s. You can save this graph file. Save as. Let me give the name. This is dos.agr. agr, and press OK. Pass it. Where is my agr file? Here, this one. You can directly see it from here now. A problem with this. Here is. Now, I want to plot band. For band, first we need the band lines. For that, what you have to do, you need another utility, that is XV to XSF. So for that, you have to again go to your Siesta, then util, and check for XV to XSF. That is inside this concave. Same Posnokov. I'm repeating it again. You have to go inside Siesta, then util, then concave, again Posnokov, then open terminal here. Type ls, because we already did it here, make the FMP DOS file, and this XV to XSF file is already created here. But we need to copy it. So again, the same command, sudo cp xv to xsf. Then I want to copy it, user usr local bin, then enter, type your password, and done. I'm copying. Let me paste it in this chat box. Where is chat box? Okay. Now, what we will be do, let's back to our directory, open terminal here. We need a path, reciprocal we need to choose a path to plot the band. For that, what you have to do, first type ls. Let me first show you once the simple way to choose the path for band, high symmetry path. You need CIF file. And you need one website that is CK path. Just open a Google and type CK path. And the first link will be me paste this link in your chat box. The website name is CK path. For that, you can see here, it can read a file that is CIF file. So to create a CIF file, just open a terminal here. Okay. What we have to do, we have to open GDIS, then our FDF file, that is carbon.fdf. Hit enter. Now save your file as a CIF format. Let's say carbon. From here, you have to choose the format CIF. Okay, save it. Done. Pause. Now go to this website. Choose your CIF file. From here, if you click here, just below choose file, from here you can set a CIF, choose file, and choose your file from your directory. Open and calculate my structure. Go down. This is your, go down. From here, if you double click, you can see your brilliant zone, and the suggested path is here. Like it is saying gamma y c naught, or this back to gamma. Then you can copy this path from here, like gamma is here, then it is saying y is somewhere here. You can copy these lines and paste it in your FDF file. Where is FDF? And paste it in your FDF file between these blocks, band lines. The first one, they said gamma, then the second one is y, the third one is something, and then back to gamma. But I want to show you another way how you can manually choose this path. So first, what you have to do, you have to convert your XV file to XSF format. So how you will be do this? You will be you need that utility XV to XSF that we copied from the Siesta util. Then run this XV to XSF. Then hit enter. It is saying specify the system label. So system label is here is Siesta.xv is the extension. It is saying only specify the system label, only the system label. So the system label is Siesta here. Press enter. It is saying found and open. Done. Now type ls. You can see a file that is XSF file is created here in your directory. Now let's open this file. How you will be open this? Using xcrisdone. We installed the xcrisdone in the day one. So how you will be open this? Xcrisdone, then dash xsf space star dot xsf. Let me copy it. Xcrisdone space dash xsf in small letter space star dot xsf and hit enter. You can see your carbon FDF file here. This xcrisdone is very good tool to visualize your structure or relaxed structure, and you can calculate the bond length if you want to calculate like in angstrom, in Bohr. Let's say I want to calculate the distance between this carbon and carbon atom. Just press on both carbon 1, carbon 2, and done. You can see it is saying the distance is 1.43 angstrom and this much Bohr. Anyway, so we want high symmetry path for our this structure. So how you will do? Go to tool and K path selection. I'm repeating it again. You have to press this command xv to xsf, then enter your system label, and then open your xsf file using xcrisdone, then go to tool and K path selection. Now you have brilliant zone here. So how you will be choose your point? The first you will be start from this red color. That one, this one is the gamma, your center point. Then you can go to anywhere. Let's say I want to go here, any path. Then I want to choose this one and then back to gamma. You can select many you want, but I just selected four point here, gamma, and one here, let's say M, then K, and back to gamma. The center one is the gamma, your center point, that red color. Should I repeat it again or you got it? Anyone have any issue up to this? Okay. So now here you have a value, something that is reciprocal coordinate 0, 0, 0, 0.3, 0.30, 0, 0.5, 0, 0, 0, 0. So what you have to do, you have to enter this point in your FDF file. First, uncomment all these tags that we commented before. I'm going to uncomment. Okay. The first one is our gamma, that is 0, 0, 0. So let me delete it. The first one is 0 0.00, 0 0.00, 0.00. And let me give the name. It is gamma, GAMMA. My second point is here I am writing 50. 50 means I started from let's say from 1, and the distance between here to here is 50, or you can say integration between the point 1 to point 2 is 50. Then the coordinate of the second point, that is 0.33, 0.33, and then 0.00. Let's say this point is M, or you can give any name. Then M2, that next point, I want, let's say it is again the 50, 0, it is 0.00, then 0.5550, and 0.00. Let's say this point is K, and then back to gamma, that is again 50, and 0.00, 0.00, 0.00. I'm saying this is again gamma, gamma, too many K. And save it, save your FDA file. So cross it, your expression, cross it, save your FDA file, and run the Siesta again. Siesta less than my input file name, that is carbon.fdf, then TWE, and output file name, that is log.out. This thing you have to do after the optimization. To do the complete optimization, first you have to optimize the mesh cutoff energy, then the K point, then the lattice constant, and then the final optimization. Then you can do these things. Done. Hit LS. You can see a file that is band.siesta.band is created here. Siesta.bands. So if you open this file, Siesta.bands, where it is. Siesta.band. Now you can see that in this band file, the first one is your Fermi energy, and if you go end of this file, you have high symmetry point, that is gamma, M, K, and back to gamma. Okay, so what we do here, we need a utility GNU bands. For that, you have to go back to Siesta, then util and bands file, and open terminal here. First, let me clean it. ls, what you have to do, you have to type make. For GNU bands, what you have to do, you have to go Siesta, util, and then bands, then open terminal and type make here. It is saying nothing to do, nothing to be done, because I already did it. So now you have to copy. If you press ls, you can see a green file, that is GNU bands is created. You have to copy this GNU band to user local win sudo. How you will be copy? Sudo cp GNU bands to user local and win. Press enter. It will ask for password. Let me post it in the chat box. Okay, So let's back to our directory, working directory. So open terminal here. And you have to press GNU bands, then the less than, and your band file name. So what is the band file name here is siesta.bands. So let me write siesta.bands, then this sign and T, then you have to write bands.dat or bands.txt. So bands.dat. Okay. Okay, and press enter. Done. Now type ls again. Ls, you can see the bands.dat file is created here. Now plot it using xmgrace. So how you will be do xmgrace bands.dat bands.dat and enter. Bands, not band. It is xmgrace bands.dat. Enter. Again, you have to just 1 minute. Yes. So what you have to do now? First, you have to shift the Fermi energy. Someone. Good. Kedar is posting something. Kedar Verma. Okay. So how you will be shift the energy? The same step we have to follow. Just open that bands file, siesta.band file. Sajil sir, good. Siesta.band file, where it is siesta.band. Here it is, siesta.band. The first one is your Fermi energy. So you have to shift the Fermi energy. So how you will be? Just go to data, transformation, evaluate expression, click on any set and press Ctrl A to select all the band line, then the second one and press Ctrl A. Now again you have to enter a formula that is y is equal to y plus your Fermi energy. The Fermi energy is 5.04713 something 36, and make sure either press on apply or accept. I'm going to press on accept. Done. Okay. Now set your range. Just double click on y-axis. You can give the label here. This is energy in electron volt, and you can set the this y-axis range. Let's say I am interested only in -10 to +10 range. Press on apply. Okay. And one thing, you can decorate it whatever you want. And the major step is one major spacing step between this line -10 to +10. How you will we do this? Just double click on y-axis, this line, double click on it and set the range, set your major spacing range. Let's say 2 here. Then you can see the step of 2. Then go to, from here, go to x-axis. From x-axis, we have high symmetry point along the x-axis. So we don't need the label in x-axis, because in this axis, in this y-axis, we have high symmetry point. We will draw that high symmetry point in y-axis. So what you will do? Just we don't want the display untick this display tick label, display tick mark, display axis bar. Just apply. It will be disappear everything from here. You have to go along x-axis and untick this display tick label, display tick mark, display axis bar, and press on apply and close it. Now just double click in your graph, inside your graph. Just double click on any line. It will appear a kind of, you can see here. Just press Ctrl A. I want to increase the width of this line, so just double click on any line, then press Ctrl A, and you can increase the width from here. Press apply. You can change the color as well. Let's say black, or let's say blue, like this. But I think black one is better. Okay. Now the important point is here. When you go to the end of your band file, you have high symmetry point that we need to plot in your x-axis. So here, how many points we have? 4 points: gamma, m, k, and gamma. Here it is. So we need to draw the line. Like the first one is on 0, that is gamma. So we have line here. So we don't need gamma line. Then we need m somewhere here. Then the k line, and the last line, it is this one. So first, double click on your x-axis and stop your x-axis at the maximum point of your gamma, that is 2.09, 0688. Press apply. What I did, double click on x-axis. My x-axis is started from 0 to this point, that is 2.09. So I press 2.09, 0688 and press apply. Now we have gamma here and the last gamma here, but we need 2 more line, m and k. How you will be plot these lines? What you have to do, go to data, go to plot, not plot, go to window. You have to go window, then drawing object. You have to go window and drawing objects, because I have problem with the screen. Yes, this one. A kind of box will be appear in front of you. Here we need a line, two line. How many line we need? Two line, because we have 4 points. The first one is your starting point. Then the second one is our ending point. Then we left with two more line, that is M and K. So first click on line properties. Here you can see, you can write text properties, text properties, line properties, box. So what we need line. So first click on line and draw a line, any random line, just draw it. And second one, same 2, and 3 line I draw. 2 I need in x-axis. 1 I will explain why I draw the third one. Now click on edit object and click any one of the line that you draw. Just click on it. A box will appear in front of you. A box like this one. So here, first thing you have to do to change the position of your coordinate from view to world coordinate. Make sure, I'm repeating, you have to change your position in view coordinate to world coordinate. Then you can change the line color if you want. That I want it in red. You can change the line width and the line style. I want it in dotted line. Okay. Now, where I want this line, this is the M. So M is 0.880345. So X1 is 0.880345. The Y this line. So you have to enter this value, Y value. So your Y is starting from -10 and Y2 is your 10. So our Y1 is -10 and Y2 is +10. Now X1, if I press apply, you can see the line is not in the straight. It is going from X1 to kind of it is, I mean, it is not a straight line. So you have to keep your X1 and X2 same. Your X2 should be same as X1, 0.82, sorry, 0.880345. Apply. Okay. Now press close. Press on second line that you draw. Again, the same thing. You have to change your coordinate from view coordinate to world coordinate. Then change the color, line width, then the line style. Your second point is K, that is on 1.320585. So let's draw the second line. That is 1.3205 and Y is same, -10 to +10, -10 to +10, and X2 should be same as X1. So it should be 1.320585 and press apply. Now it is x1 is 10 to 10, minus 10 to plus 10. Okay. Now you can draw a Fermi line here on 0 to to make your graph is more attractive, or to make it more clear where is 0. So that's why I draw a third line. So I want to make it a line on 0, therefore people can distinguish between plus value and the minus value. Let me double click on it. I want first world coordinate. Make sure you have to change it in world coordinate. World coordinate. Then change your line to red. Width, let's say 1.5. Dotted line. And now I want a line that starts from 0 to my maximum x-axis. So x1 is 0. y1, I don't want my line in y, so it is 0, 0, 0, and x2 is the maximum length of our x-axis. So what is the maximum length? Maximum length was 2.09 is 2.09, and again y2, I don't want my line in y2, again 0. Press on apply and close. Now go to text. Let me give the symbol here and press here just below from this. Just click on it. Text string will open here. So first one is our gamma. Here you can see the first one is our gamma. So in XM base, how you will be write gamma? It is you have to first enter. Yeah, make sure that change the position coordinate as well in the world coordinate, not in the view. Not make sure like in the line we change the coordinate from viewport to world coordinate. Let's do it in the world coordinate. And to write the gamma, how you will be write gamma? You have to write backslash, one backslash only, small x and capital G, and press on apply. You can see the gamma is here, gamma symbol. You can see. Let me write it in the chat box. To write gamma, how you will be write gamma, backslash and small x and capital G. Okay. Now my second high symmetry point is M. So just cross. I accepted it. Cross it. Click on here M. Now same, change the coordinates to world coordinate and write M. Press apply. The third one is K. So cross it. Click on third line. Okay, change the coordinate to world and then K. Accept. Then the fourth one is again gamma. So how will we write gamma? Backslash X and capital G. Okay. Now you can adjust it using just move object. You can move it like this. Here, 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 here. This is the band structure of graphene. So just save it. I'm going to save. And you can convert it or you can print it in a JPG format. apply, okay, file and print. This is how we plot the band. Here you can see I did it before. This is our band for graphene. Now we will do the optical properties, and Verma sir will explain the optical properties to you. Verma sir, it is over to you now.
Before that, any questions from audience? Because the offline candidates are being helped by some persons, but online audience, if you have any queries and doubt, then you should ask. Yeah, without any practice, it's not possible to bend such beautiful bend plot. So you have to do practice. Several practices needed for such type of graphs. So what we have learned in these electronic properties, especially that we have plotted DOS, density of states, and then projected density of states by using which tool you have used? FMT DOS.
FMT DOS, yes.
FMT DOS, and there is another tool also. You can also plot this PDOS by using PDOS XML introduced by ma'am, and also the one tutorial is available in my YouTube channel. And that related to COOP, one recent video is uploaded by me, and by using that COOP utility, that is MapRock COOP utilities, and you can also plot that PDOS, and I have performed the same in my channel. And about this band plot, in physics point of view, you must know about that crystal structure, symmetry points of that crystal structure, reciprocal lattice, and why we are using that reciprocal lattice, and that EK diagram, what is that EK diagram, etc. So for the fundamental, for the basic, you must know about all this. So that is available in Petal's book. So you can follow all this. So crystal structure, different type of symmetry points, and reciprocal lattice you must know. As well as that band gap, it is very important, and that direct and indirect band gap type material, it is defined on the basis of this band plot, and you know from the definition, if that the gap between two points it's less into different k point, then that is indirect band gap. Just if you plot that band gap from, in spite of this graphene, if you plot this for silicon Si, then you will get indirect type of band gap, because silicon is known as indirect band gap type semiconducting material. And if you plot this for gallium arsenide and this graphene terms, then you have this is that direct band gap type material, because that peak, and this is also zero gap band gap semiconducting materials, graphene is, and this is very wonderful material. So because of this band gap, this is a very good, it is known as very good material. And even some more things can be performed on this band plots also, that at a different fed band utility is there to show that contribution of different orbitals in the different conduction and valence band. So by dividing this band in two parts, one below that Fermi energy level, above that Fermi energy level, we can classify conduction and valence band. And the contribution of orbitals, one can check by fed band plot, or just observing that our PDOS, and comparing with that PDOS plot with that band gap, we can confirm that which orbitals are contributing their role in that conduction band or valence band, and the properties of that materials can be analyzed by using this. So I think there is any questions regarding this DAS, PDAS, then, and I also want to discuss about the charge density plot is also required, but in general, we are just leaving here. Narendra, can we plot charge density if we have time? No.
Yes, but
It's
no, sir.
free.
We have only 30 minutes, 30 to 35 minutes.
30 to 35. So just leave it. Okay. So if you want to plot this charge density, that very wonderful, beautiful plot, colored plot, and for that you have to use row to XSF, and that is and then that XSF is observed by using X crystal. So you can learn this by using my tutorials available in my website, as well as that from this my YouTube channel. Now next part is let's have that optical properties. So theoretically, this optical properties was well explained by Professor Avidya ma'am, and we just provide that material and calculate that E2, and by using some mathematics, some optical properties are analyzed, and optical materials, nowadays optical materials are very important materials, and transport properties. Is it possible to say something about transport properties? It's so big, and so many things have been discussed by especially Sajal Biswas. So many things have been discussed by that
Right, sir.
Dr. Panda, and also I have given some glimpse. So you should follow Dr. Panda's video for that transport property, especially.
Okay, sir. Okay, sir.
And actually, that designing of electrodes, and then this active materials, it is well given by Dr. Panda's video. And one is scripts. I have some scripts to run this transport properties, that using that old version of Siesta and a new version of Siesta. Okay, so okay, we will work Dr. Sajal Viswas, and I know you are doing good. So definitely
Thank you, sir.
you will do much better of your as per your expectation. Okay, so I think let me proceed that optical properties. So should I share my screen? Host disabled participants screen sharing. Please allow me to share my screen.
Yes, sir, you can share now. Your co-host.
Can I? Okay, good. So my screen is now visible. So on my screen, I think you are able to observe so many things. That one tool, that is Argus Lab, and Vesta is here, and all these are window based. And this is that GP medium. Yesterday in my lecture, I have mentioned this, and I am since I am using that virtual window, so that virtual box is also here, as well as this is another tool to study that same HTM image, and that HTM image is that this term is used by Dr. Rodrigo. So let me open my virtual window. So this is that virtual box in which I am just running Siesta just for post processing and some calculation, basic calculation. I have 4 nodes in my this laptop, so I can. So let me show you that Siesta. This is that folder where that Siesta is available, and the version of the Siesta is 4.1.5, and I have mentioned that this is a well documented software, well documented tools. So we have this documents part in this folder, and second, some examples, good examples are given to learn with this readme file. And if you are using Google as a guru and learning Siesta by using this documentation, then you can just learn from these examples also. And this is that objective directory where Siesta is compiled, and that binary file is available here. And this binary file is now linked to bin directory. So I think in my tool that Siesta is running as Siesta.exe is running, I think. Let me check. This is Siesta.exe. Okay, so Siesta.exe is a binary file available in my system. Arun, so that Narendra has using Siesta, so I will use the Siesta.exe. Okay, so I was here. Okay. And many text files are here for depending on the different properties. So if when you went through that tutorials given by Siesta developers, then you can go through this. You can learn so many things, that burn, what is that burn is, force constant, what is that, how one can apply this gate voltage, gate heart rate to the particular system. Because if you want to study that some devices just like FET, felt effect transistor, so for simple diode you have 2 electrodes and you can run transistor, and for third third electrode you have to apply that gate voltage in a particular direction. So you can use this, and every folders will have one FDF file, and pseudo potential file is given in form of this link, and one can run all this. So many test files are there, and Siesta learner should follow this variable, say in transistor, and that spin orbit coupling, etc., etc., etc. So we have different properties. Another one property is that magnetic properties one can study, and the next one is that yes, this I just forgotten to about this utils. So this is another directory where different utilities are available. So for bands, you have used this band utility, and simply you can optimize this by using Mac command, a single command, and then in the country. There are so many utilities that by given this Siesta developer, and one can optimize this. One can this compile by using simple Mac. The Mac first let me clean and Mac. So you will have different utilities compiled by using a simple command, and all these binary files are available here. So this EIG to this FM, you have used this row to XSF. You will have to use for charge density plot, and XP to XSF you have used for getting that symmetry points K path by using this tool. So and one can use, and for animation one can use this AMD to XSF and other things. Anyways, so now that tutorial day number 3 I have downloaded from the same folder given by Mr. Narendra, and where that T3 this is exercise number 3, and this is T3 tutorial. So here I would just like to mention that for a particular property you need different flags to add in FDF file. So for optimization there are some terms you are using in your FDF file, that is the basic information of that material, system name, system labels, number of species, number of atoms, and then this atomic number of that species corresponding. Then these K points, you have optimized these K points by using my script, and then these are the lattice vectors, and also the lattice parameters are lattice vectors, and you have optimized this by using that script. And this is the coordinates, and these coordinates are in different form, and you can go through that manual, system manual for different format, and generally I use that fractional format, and some constant can be used to fix some atoms, and these are some fundamental terms, and this LDA, this is exchange correlation function, number of pulley and CG steps, etc. And this row save row, this will give that row file, and this can generate by using that row to XSF. One can generate XSF files for charge density plot, and different terms are there. For especially and for band plot, you have used that block for the right bands with right bands, and for pdos you have another flag for pdos, and coop for coop you have to use coop dot right true. So several flags depending on the properties you are using, you have to add. But adding these flags, it is you have to perform this adding only after the optimization of the system. Otherwise, computational time will increase. So first step is design the material, create MDF file, optimize that MDF file by using that 3-4 steps, and after optimization you have to use for further studies. So for optical properties studies, this is that flag we are using, this optical calculation true we have to mention, and then these terms, these are the terms which we have to add here, and this is optical mesh, just similar to K points. It for the accuracy one can use, and this is that optical vector. This optical vector is actually this actually gives the direction of polarization. If you want to polarize that system along x-axis, then you have to use 1 0 0 depending on the type of the system. If you want to polarize that system along y-axis, then you have to use 0 1 0, and if you want to provide polarize that system along z-axis, then you have to use 0 0 1. Sometimes if you are in general, if you use any planar structured material, then that polarization must be first along the surface and second normal to the surface. So if when you go through some article related to this optical property, then that optical properties, specific optical properties, it is mentioned in terms of towards the surface and normal to the surface, or the direction depending on along x-axis and along the z-axis to observe, to see that that particular phenomena or that particular behavior is isotropic or anisotropic. If it is direction dependent or not. If similar results are there, it's okay. If different results are there, then why that result is there? So you have to explain that. And then some terms have been already discussed in the morning lecture on optical properties and broadening. This broadening is similar to that broadening in DOS and PDOS. And in general, if you want to have a sharp peaks, then use that 0.05, 0.1. And if you are that is smooth plot, then use some higher broadening. So that optical property, it is good for this broadening 0.2 or 0.3. It's good. It looks good for 0.3. And this is that optical range you have to calculate from 0 to 20. So for visible range, if we want to have, you can check the calculation. So if 0 to 5, this is that up to that visible, and that's beyond some visible range, higher range for higher range. So in general, this is that default value. And I have just copied this value from one of the test file available in the test folder of Siesta package. So this is the term which we have to add in this FDF file to run optical properties. So actually, this is time consuming. That's why just I am here giving only that demonstration part, what we have to do. So first we have to add all this, and then we have to run the system. After running Siesta, this will create another file, and just I should go through the next folder, that solution folder. And, I think this is yes. So after running this file here, this is the same file, I think. Yeah, this is the same file. After running this, we have one special file generated, that is this one, AGI mole and IPS IMG, epsilon imaginary, that is E2. So this IPS IMG, it is generated after successful running of this. And for x-axis, you will have one IPS epsilon img file along x-axis, for y-axis, z-axis. So you have to run this 3 times per 3 different direction, or 2 direction at least one should run. So this is the output file in terms of this optical properties, and there are the terms, and here the range is given, and here this is for one spin. So one spin is this epsilon rule. So you should go to the theoretical part to understand on this. So this is that IPS img file, and this will help to find find that required parameters related to optical properties, and obviously we have to use some post processing tools similar to that GNU bands and AIG2DOS and pdos XML. That utility is also, post processing utility is also available for this, and that post processing utility is available in again in this folder Siesta in. This one is very dominant, that this one is that optical. So this is that optical term, and let me open this on. So here we have 2 binary files, optical and this one, and before that one should also read the readme file. I generally recommend and request all the participants as well as Siesta learner that when you go through such type of any tools, just to try to search, there will be some readme file, and in that regarding that particular tool or utilities, information is mentioned in that readme file. So let me open this readme file, what information is therein. So here this is that system level, that IPS img file. It is obtained after running successful running of Siesta without any error, and then this 2 small programs are there. One this optical inputs.f, and there is another optical.f, and you have to compile this. And to compile this, either you can use any Siesta compiler if you know that gfortran command, or it's a simple to use a single command, that is the mac1. So let's have ls already compiled. So let me clean this mac clean. So now there is no optional file. So here this readme is here, and that this is one file available, that is optical underscore input, and there is another one, this is that optical f. So we have to compile this. So let me use that command, that is mac. Okay, so in few seconds we have now these 2 folders, optical and optical.input, and by using the same method we have to copy this optical and these 2 tools in the bin directory, and this has already been copied, and I'm not using that command now. So let me use this post processing tools in this tutorial, that day 3, and where is that? Here is that, and this is the point. Let me copy this for. Let me create that data. I'm creating this folder by using that mouse clicking method. So this folder is created by command mkdir, and you have learned so many so many Linux commands in the first day. But I just mentioned that nowadays that Ubuntu is the Linux is very user friendly, as similar to Windows. So you can use mouse to click here and there and paste. So copy paste method I am using here. So this is that file. Now first I have to use by following that readme file. I think it's open. Yeah, this one. So first I have to use this command optical input with this IPS img. So let me use this. So this is optical input with this S and ASI to this. So this will now enter it. So okay, so this will generate some lines, and then the second, that is optical only. Just type another file, that is optical. So yes, this is metal or not, you have to enter either 0 or 1. So let me press 0 here, and now you will have good number of data files. So these are some files generated by this post-processing tool, and we have two post-processing terms. One is optical input, and second one is optical. So this one, the first one will give absorption coefficient. This is related to absorption coefficient. This will give optical conductivity. This is reflectance, the known parameters which we have to use, and this is refractive index, that epsilon imaginary dielectric constant. This will give real dielectric constant. So we have all these terms useful for any research article. So again, now let we can plot XM grace by absorption coefficient. So this is that plot. This is that absorption coefficient. So along y-axis, this is absorption coefficient in arbitrary unit. Along x-axis, this is that energy terms from 0 to 50. And now you can decorate your plot. And generally, in absorption plot, experimental person create this absorption plots in terms of that wavelength and absorption parameters. And here it is developed for energy and absorption plot, and one can convert this for the wavelength also. So this is absorption, and then next the conductivity, some rays conductivity. So all the output file can be plotted here. So this is that conductivity plot. So one can see at a particular wavelength or energy, it's how good conductor or not. This is optical conductivity. Then some rays, refractive index, reflectance or refractive. Let me check refractive index. So this is that refractive index. So at the zero frequency, this is that refractive index can be calculated. And as a terms of frequency, how this refractive index changes can be observed by this plot. So this is very simple method. Only thing that is required is some more computational time because it takes time to polarize the system. So that's why only demonstration part is here, and decoration part is on your hand. How you can decorate all this. So this is a good tool, and some simple figures from one of our paper. It is a decorated figure. It's a for different just by using data import method, and this is the transformation of silver iodide to copper iodide, and change in imaginary dielectric constant. It is shown in this particular plot at 0 to 12 volt, and some 4 parameters are here mentioned here, and other parameters. So this is the term. And also, if I have just 10 more minutes, so for the magnetic property, I have that demonstration. Let me check what are available here. So magnetic properties here. Okay, let us check what is available here. So in the magnetic properties, what we generally add in this input file, where it is that FD file, this one. So all terms are the terms. One, I think, is this? No, it's a big one. Let me check the real. I think I have deleted one. So one term that is spin polarized, it is included here. Somewhere, yeah, this one. So this is spin polarized true. It is additional line added in FDO file to get this magnetic properties. And when we add this and run the Siesta program, then this creates this gives us some extra data for the second spin. Generally, at 0 spin, your first spin is used in general. For when using this, after running, you will get some additional lines. This is old file, so this one, that is spin moment line, it is appeared in that output file, and this give magnetic moment in Bohr magneton. So 2.88 Bohr magneton is given by this Fe molecule, single molecules. And how one can we can get this is giving a spin the magnetic property or not. It is shown by some plot, spin up and spin down plot. If you spin up and spin down a plot, these are not symmetric, asymmetric plot, and the peaks are not cancelling its behavior. If you spin and spin down are different, means this will show that magnetic property. So here its magnetic property is shown by Fe. So it's a very simple run, and it's not time consuming. Just to use spin polarized. After optimization or before optimization, just mention one term, the spin polarized, and you can optimize the system, and this will give. So qualitatively as well as quantitatively, one can get that magnetic properties. And even if we have for the magnetic properties, we have different tools associated with this. That one is non-collinear magnetic properties, and that orbital spin orbital coupling to show the behavior, as well as the simple that the dust plot. Even by using that pdos plot, one can give the contribution of different orbitals in spin properties. So which particular orbital is showing interest to show that magnetic properties can be observed by this pdos plot. So you can use DAS, or simply by using this DAS, or if you want to go to the details, then you can use pdos plot. So I think now let's start that discussion session. So anyone want to say something, then we can discuss, because we tried to do some perform some hands-on on some tools of this system, and how we are successful. It depends on the feedback from the audience, and so I think now it's over to you all. Thank you.
Now session is open for session. If anyone have question, then you.
Yes, Narendra, just in the morning session, I have requested to you that you have to give some lines to the MSc student, especially
Yes.
to the importance of this molecular modeling as far as the PhD programs at different universities are concerned.
Yes, sir.
So give your opinion. 5 minutes. Yeah, you have 5 minutes.
Okay. First, thank you, sir, for giving me opportunity that to participate in this hands-on session. Actually, I'm Narendra Kumar. I did my master from Himachal Pradesh University. Now I am doing a PhD in UAE University, that is in Abu Dhabi. So I start molecular modeling in 2019 with Dr. Arun sir. So in that time, I don't know how to start. I was just an average student, and I don't have as good physics. My background was very weak, but I start learning some basic. What is Siesta? Start doing some calculation. Then I joined Verma sir lab as a project fellow for 6 months. We learned many things there. how to publish paper, how to write, and many some basic things we learned there. And the one thing that I missed here, that I enjoyed in SSTC, is the environment of doing research. The environment here is kind of constrained, but in Verma sir lab, I enjoyed a lot. We even used to stay in the lab in during the night all the time. I mean, the kind of, the how he explained the thing really inspiring me. Then after that, Verma sir said one line to me, that is कि जो बरगद के पेड़ होते हैं उनके नीचे पौधे पनपते नहीं है. और मुझे वो लाइन बहुत ही इंस्पायरिंग लगी थी उस टाइम. that I thought that before that my inspiration is kind of कि जो बड़े इंस्टीट्यूट में जो लोग होते हैं वही शायद कर पाते हैं रिसर्च में. बट जब मैं सर की ये लाइन सुनी तो I was so inspired. Then I start to apply abroad. First I applied in Czech Republic, then I got rejection, then I applied South Korea, and many countries I applied. But somehow I got a research assistant position in UA University, where I have to work with the experimental people as well as with the Dr. Gupta sir. And after that, I applied for PhD, and now I'm doing the PhD. So the motivation is to learn basic thing there. You can publish a paper. On the basis of your research, people can hire you. Don't think that you are from a government college or from a small institute. People know you based on your work, what you have. That's all. Thank you.
Thank you, sir.
Thank you, ma'am.
I would like to thank Professor Mohan Verma sir and Mr. Narendra Kumar sir for helpful hand-on session on Siesta. Now for valedictory, again I welcome you all. Now I would like to invite Organizing Secretary Dr. Alok Luka sir, Assistant Professor of Physics in Government Nagarjuna PG College of Science, Raipur, Chhattisgarh, to read a report on 3 days workshop. Please, sir.
Thank you to all and welcome. Myself, Dr. Alok Luka, Organizing Secretary. So this is the 3 days detail here. Government and Nagarjuna College of the Science, Raipur in the Physics Department, organized 3 days international workshop on experimental and simultaneous solution of the developing naval sustainable material from date 8 to 10 February. This workshop was held in the hybrid mode. Here national and international research scientists and the professors of the 7 different countries such as the USA, US, Sweden, Abu Dhabi, Saudi Arabia, Brazil, etc. and from IITs and NITs have joined hands on various topics. The detail of the first day is, first day inaugural talk was given by the Professor Ravindra Pandey of the Michigan Technical Universities of the USA. He is the one who laid foundation of Siesta simultaneous workshop in this region. Thereon, Professor Mohan Verma sir from SSTC Bhilai took practical sessions on the methodology of the simulation And the GNSC has signed a MOU with the SSTC Bhilai, SSTC along with GNCSC. Help for the offline practical session. Also, the Narendra Kumar from Abu Dhabi also guided students in hands-on session. Professor Namita Brahme and the Professor D.P. Bisen from the Department of Physics, Pandit Ravi Shankar Shukla Vishwavidyalaya Raipur were present as special guest in the program. Now the entire program was conducted under the guidance of the principal Government Nagarjuna PG Science College, Professor P.C. Chaube sir, and the Professor Anjali Abadhiya ma'am, who is the head of the department, and the chairperson along with Professor Vinod Dubey sir, and the Professor Samit Thakur, myself Dr. Alok Kumar Luka, and Mrs. Manisha Gupta, the technical team, and Mrs. Rashmi Topo hosted the whole workshop, and other professors, Dr. B.K. Verma, Dr. B.G. Sharma, Dr. P.K. Devangan, and Dr. Neetu Singh of the department also supported. Entire program was sponsored by the CG Cost. Speakers during 3 days of the workshop were Dr. Rodrigo Emoriam from the Brazil, and the Dr. Milind Rane, IIT Mumbai, Professor Anshuman Dhalvi, Beats, Rajasthan, Dr. R.K. Gupta, Saudi Arabia, Dr. Preetam Panda from Sweden, Dr. Manvendra Tripathi, NIT Raipur. Total 128 participants from the different institutions of CG, and the 7 other states had joined the workshop via online and the offline mode. MSc 4th students Akansha Patel, Vinay Patel, Arbaz Sheikh, Megha Mishra joined the organizing committee and made the program successful. So thank you very much to all of you. Thank you.
Now, I would like to invite chairperson of this session and workshop, Professor Anjali Abadhiya ma'am, to address all the participants. Please, ma'am.
Namaste, and welcome to the valedictory session of this 3-day workshop. I'm really overwhelmed to conclude this workshop. All 3 days we enjoyed, we learned together, and it was really a very nice experience, because this kind of workshop, which is a very technical thing, we can give lectures and we learn nothing. But in workshops, there was hands-on practice all 3 days. And I'm sure that the students and the participants who joined online or offline, all must have been benefited by the rigorous training given by Mohan Verma sir and Narendra Kumar. So here I am for thanking all of you, the heartfelt wishes and my gratitude, showing my gratitude to all those who joined hands to make this program a success. First of all, I would like to thank Professor Ravi Pandey sir from Michigan Tech University. Actually, he initiated this Siesta training workshops at Raipur, and we all learned from him. And because of his constant guidance and inspiration, we were able to take up this program to this level. Secondly, without Mohan Verma sir, it was not possible for me to organize such kind of workshop, because his expertise in Siesta, he is a self-taught person, and he always supported our students unconditionally throughout these 4-5 years. And our students could do projects, and we designed several Siesta-based experiments, due to which even while we are facing the problem of lack of sophisticated instrumentation, but our students are doing what IITians are doing. So I'm very proud to share. I always share this with my student that you are doing what is available only at NITs or IITs. So as Narendra Kumar said, it is not always that if you belong to a good institution, a reputed institution, a state-of-art institution only, then you can excel. You can excel from anywhere. So I would also like to thank Professor P.C. Chaube sir, principal of the institution. He is also a physics person, and he always granted us free hand for organizing such kind of academic things in our department. Navita Brahme ma'am and Dr. D.P. Bisain sir from SOS Physics, Pandit Ravi Shankar University. They have been like buddies for me, and they have been there for me always and for all of us in the department. And they were there to grace the inaugural session. So I'm very much thankful to them. I would like to extend thanks to CG Cost, who is the funding agency. Without their support, it was not possible to organize this program so gracefully. And the one person who amazed us with his skill is Dr. Alok Luka. His technical support, and he was in the role of moderator. And his technical support was amazing, actually. I knew that he has an experience of FB Live. He's there always on FB as a live performer and content creator. But here, because it was a hybrid mode and we were organizing such a program for the first time, so it was awesome to see that a person of physics can handle all these technicalities so beautifully. So I'm grateful to Alok. Without his support, it was not possible for the department to create such a great event. Then Dr. Vinod Dubey and Dr. Sameer Thakur, they were in the role of conveners, and they supported like anything. You know, if you want to organize an event, it's like a beti ki shadi. So we have to arrange a lot of things. They were there in night up till 10 to 11. They were there in the morning to receive our guests. From morning 7:30 or so. So you students may not be knowing what was going on at the backdrop. So we were working together, and they supported this program like anything. Then we have our students. Students are our strength. You are our strength. Youth is the strength, actually. So we have some students who are doing Siesta, and they are very well they are experts in Siesta. I would say they are not expert, but they are learning Siesta, and they are in close contact with Mohan Verma sir also. So because here they actually conducted the hands-on session, they guided the students, because Mohan Verma sir was here for one day only, and last 2 days these students, Vinay Patel, Arbaz Sheikh, Akanksha Patel and Megha Mishra, they were here to support us, and all our PG students were there because MSc final students have already done Siesta practicals. So, but they were there for showing their support. So I'm very thankful to all these students, and the UG students, previous students who participated wholeheartedly. They learned a lot. And also, I would thank Kusumanjali ma'am and Nagbhargavi ma'am from Dharsiva College, and Kusumanjali ma'am from VYT College, Durg, and Neelam Shukla ma'am from Kalyan College. They sent their students, and 40-50 students were there. And again, SSTC was there to help us to organize the offline hands-on sessions at their campus, and they provided the computer facility and all to those 30 students who were participating from Durg itself. Then at our college, we have a small simulation lab, but students came with their laptops and they could learn, and they had a good experience. I hope that they learned a lot from these sessions. Last but not the least, one more person who came triumphantly was Rashmi Priyatopo. She was there. She was very attentive. She is very sincere, and she actually was in a role of moderator, and I saw that all the time she was there to see that if there is some disturbance, to mute or unmute anybody, or even conducted the whole program beautifully. So we have a good hand in our department. Manisha Gupta, I would also like to thank her because, it was the first international workshop and which was to be held offline, and we wanted to give it a good look, good presentation to our high tea session. And she decorated it so beautifully that it really gave international, because I have attended a few international conferences and I saw that the high tea was up to the mark. So I thank Manisha for that good presentation of high tea, and it was liked by one and all. Last but not the least, our support from class 3 and 4 staff members like Bhuneshwari, Dhruv, Birbal Verma, Vijay Devangan, Semesh Verma, and Chotilal Porte. They were like, they were there for us all the time. To fix a little thing like this door of the opening door of this e-classroom, to fix the flowers in place, they were there in the tea session, in serving, and in helping our students also with all the things. So it's a teamwork basically. And I think this is just a beginning. And I know that Mohan Verma sir and our department will be there for all the participants all the time. This is just a beginning. You have just started learning Siesta and the modeling and simulation. So whenever you have any difficulty, we will be there to support you. This I assure you. So thanks to one and all, and bye, and see you in the next event.
Yeah, one person left. That Renu was handling the sister from SSTC lab.
Right.
With so thanks to Renu.
Yes.
Engaging the students, 30 students in 12 computers. Anyways.
Like to say a few words on this occasion of valedictory. Did you listen? Verma sir, would you like to say a few words?
No, I have said so many things, and one thing is just love to learn a sister, and if there is any problem, just we are always here. Just message me. You can mail me, and I love learning. So I am also learning. So now we are just attending to learn machine learning and association of this machine learning with this DFT tools. So learning is always open. And if you want to be energetic always, then you should learn always. So please keep learning and enjoy learning.
And our institute and our students would love to learn machine learning with you and your team. So thanks to all and good day.
Thank you all the participants to make this workshop successful. And
sorry, I missed to thank all the speakers who joined from all over the world. Dr. Milind Rane from IIT Bombay, Dr. Rodrigo Amorium from Brazil, Professor Anshuman Dalvi from BITS Pilani, Dr. R.K. Gupta from UAE, Dr. Preetam Kumar Panda from Sweden, Dr. Manvendra Tripathi from NIT, and of course our own Mohan Verma sir. So I thank all these speakers for sharing their expertise and giving an exposure to our students, the world-class exposure they could give. Thank you.
And all the participants are requested to fill the feedback form that is compulsory for the certificate. And if any of participants want to share their experience on this workshop, then you are most welcome. Any participant? Those who has joined online, they also can share their experience. Sejal Vishwas sir.
Yes, ma'am.
You can share your experience.
Hello. Am I audible, ma'am?
Yes, sir. You are audible.
I'm very happy to join this program, and this is a great opportunity for all of us for learning from the legends. Siesta is though siesta is a very difficult thing, I think, but as respected resource persons have nicely explained all the matters, and it is quite clear to all of us, and hope in near future you will be able to organize such kind of wonderful hands-on activity session as well. Thank you all.
Anyone else? One of our students want to share his experience.
Hello, myself Vinay Patel. तो जैसे कि हम अभी 4th सेम में हैं, तो हमने पहले ही प्रोजेक्ट प्रैक्टिकल कर चुका है इसका का। तो पहले हमने एमएल मनुष्य के बहुत सारे वीडियोस देखे हुए हैं, तो बेसिक आइडिया हमको वहां से मिल गया था। बट फिर भी अभी जिस तरह का सर ने नरेंद्र सर ने हमको समझाया है, स्टार्टिंग फ्रॉम द कमांड्स दैट इज मोस्ट कॉमन सीपी कमांड कॉपी होता है, एलएस लिस्ट होता है। तो स्टार्टिंग में हमको ये सब चीज़ नहीं पता था। तो इस सेशन में हमको वो बेसिक चीज़ों से लेके विद एडवांस जैसे जेएनयू बैंड्स जो हमको भी नहीं पता कैसे प्लॉट करते हैं, तो ये सब चीज़ बहुत अच्छे सीखने को मिला है। तो होपफुली जो ये इंटरनेशनल वर्कशॉप है, ये इन फ्यूचर जो बच्चे प्रोजेक्ट करेंगे या प्रैक्टिकल्स करेंगे बहुत हेल्पफुल होगा। तो थैंक यू वंस अगेन नरेंद्र सर एंड सारे सर जो ये एक्सपोजर और ये मौका मिला कि इस अटेंड कर पाए इस इंटरनेशनल वर्कशॉप को। थैंक यू सो मच सर।
So thank you everyone. Now we are going to end this session. Thank you. Thank you all.